Okay, so my dear students, very good morning. Today we will going to start the session now. In today's sessions, first I will going to discuss with the standard optimization model, and we will going to discuss a certain the points that needs to be considered and needs to be remembered while you are formulating an optimization design problem. And later part, we will just move on to the classification of optimization problems. So what are the different, how we can classify the optimization problems on based on different headings. Okay, let us start with the first one today. So that is the optimization problems. Yeah. Yeah. So in the previous classes, we were just discussing regarding so how to formulate the optimization design problems. So we have discussed so many problems and also with the different concepts with respect to the tank design or with respect to the can design or with respect to the sawmill operations or with respect to the cabinet design in the last class. See, in all the problems what we have discussed, the three important things. One is how to define a design variable. Second important thing is how to formulate the objective function. And third important thing is how to formulate the constraint. So now in today's class, let us start with the what is the standard design optimization model. So when you just want to solve any optimization problems, so that problem should be of a standard model. Okay, so whatever the description you have got, whatever the problem project description or details you have got, the data and information you have collected, and everything needs to be put it in the form of a standard optimization model. So this is what the slide what they are showing over here is the standard design optimization model. Okay, so let us just look at these things, and let us later part we will discuss the certain points regarding this optimization. Okay, see, the standard design optimization model will be in this form. Define an n vector x is equal to x1 comma x2 dash 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 to the xn of design variables to minimize a cost function. Cost function it is given f of x or cost function, which is a function of the design variable x1, x2 till xn, and it has been subjected to sorry, subjected to the two types of constraints here. One is an P equality constraints, that is equality constraints, and second one is inequality constraints. Okay, so once you know what is the design variables and once you form a cost function or a optimization function, the next thing is what is the constraints. So there are two types of constraints in each and every problem. One is an equality constraints and second one will be the inequality constraints. And the standard optimization model, the design optimization model, will be in this form. So subject to the P number of equality constraints, xj of x is equal to xj of x1, x2 to xn, where j is equal to 1 to p. So p can be any value, can be 1 or 2, 3, so it can have. And the m inequality constraints. So look at here. So gi of x is gi of x1, x2, which is less than or equal to 0. So look at the difference between the equality constraints. In the equality constraints, we have a equal symbol, whereas in inequality constraints, we have an less than or equal to or greater than or equal to. So that is what we call it as an inequality constraint. So a problem which is having a optimization design model, so which is having an n vector. N vector means generally the design variables which will be in the form of a vector form. So the ultimately what the solution is going to get in the optimization is x1, x2 and the xn. So means you are getting the numerical values for, or you are determining the numerical values for the design variables x1, x2 to xn. So this is the solution what you will going to get it in your optimization problems. In the sense, to find an n vector, so means ultimately once you get the solution for any optimization problems, so that solution will be in the form of the numerical values for the design variables. So then, so we're going to get the optimization of the problem, or the solution will be optimized. So here, the standard optimization model, what we are looking at the board or at the slide here. So if you look at the optimization function f of x and both the constraints, that is equality as well as inequality constraints, both these functions are depending upon the design variables x1, x2, and to xn, right? So therefore, so defining a design variables is very important in the optimization. So therefore, please be careful, because we have worked out so many problems in the previous classes. So by this time, you might be knowing how to define the design variable. You have to identify and you have to define the design variables properly. Once the design variables are defined and identified and defined, then obtaining the cost function or optimization function, obtaining the constraints is not a matter. The reason for that is both the objective function or optimization criteria as well as the constraints will depend upon the design variables, and also you formulate the functions, the objective function as well as the constraint function in the form of, or will be in the function as a function of the design variable. So therefore, be careful while you are selecting or while you are identifying and while you are defining the design variables. The utmost care should be taken. So this is a standard design optimization model for us. So now let us discuss certain important observations regarding the optimization model. Several points must be clearly understood about the standard model. So what are those? We will go to discuss one by one. Okay. So here, first one is dependence of functions on design variables. First of all, the function f of x, the cost function, hj of x, the equality constraint function, and gi of x, the inequality constraint function, must depend explicitly or implicitly on some of the design variables. It means that not necessary that all the functions, the cost function or constraint function, should depend on each and every design variable, but it has to be explicitly or implicitly depends upon some of the design variables what you have identified and what you have defined. So in the sense, there should be a relationship between the objective function and the design variable, and also the constraint function and the design variable. Okay, not necessarily that all will be involved or all will be dependent. So, but there should be a relationship with some of the design variables what you have identified and what you have defined at the beginning of the program or beginning of the stage. So therefore, first of all, the functions f of x, hj of x, and gi of x must depend explicitly or implicitly on some of the design variables. Only then are they valid for the design. So please remember here. So once they have depending explicitly or implicitly on some of the design variables, then only they are valid for the design. So therefore, the functions that do not depend on any variable have no relation to the problem and can be safely ignored. So this is a very important observation from the standard. Okay, so dependence of functions on design variables. Then the second point here is the number of equality constraints. So there is a restrictions on having the number of equality constraints. So when we look at the standard or design optimization model, so we have shown the both equality constraint as well as the inequality constraint. So of course, so the question is how many number of equality constraints can we have in our optimization model, right? So of course, it is not that you can have any number, but there is a restriction on the number of equality constraints in an optimization. So that's what we are discussing in this problem here. The number of equality constraints. The number of independent equality constraints must be less than or at most equal to the number of design variables. See, the main restriction here is the number of independent equality constraints must be less than or at most the maximum extent should be equal to the number of design variables. This is very, very, very important while you are formulating the design optimization. So be careful. So from the problem description as well as from the data, so make sure that so the number of equality constraints should not exceed the number of independent equality constraints should not exceed the number of design variables. So what happens? See, that is what we'll say P should be. P corresponds to the number of independent equality constraints, where N corresponds to the number of design variables. So therefore, so in a standard design optimization model, P, the number of independent equality constraints should be less than or equal to N, the number of design variables. If not, so then we may ask the question why. So when P is greater than N, so means if you are having the number of independent equality constraints more than the number of the design variables, then we have an overdetermined system of equations. So overdetermined in the sense the equality constraints are redundant. They are linearly dependent on other constraints or they are inconsistent. So these are the two important words. So when P is greater than N, the condition, please remember, when P is greater than N, then the system is said to be an overdetermined system. Okay. So in this case, the some equality constraints are redundant, means they are linearly dependent on the other constraints or they are inconsistent. So when you find the equality constraints are redundant, so you can delete them. Redundant constraints can be deleted, and in the later case, that is in the inconsistent case, no solution for the design problem is possible and the problem formulation needs to be closely re-examined. So this is very important. So please look at that. So make sure that the number of equality constraints should not exceed the number of design variables. Okay, so if it is greater than N, you have a overdetermined system and the some equality constraints might be redundant and some might be inconsistent. Which you find or which you identify they are redundant, you can omit them or you can eliminate them. And if you find they are inconsistent, then you have to closely re-examine the problem formulation. So this is a one important condition you should remember all this. And if P is less than N, the optimum solution for the problem is possible. This is another important. When P is less than N, the optimum solution for the problem is possible. When P is equal to N, in the sense that's what, so at most equal to. So generally what we expect is the number of independent equality constraints should be always less than the number of design variables. But maybe at certain case, it might be equal to the number of design variables. When P is equal to N, no optimization of the system is necessary because the roots of the equality constraints are the only candidate points for the optimum. So when the equality constraint is equal to the number of design variables, so no optimization is required. No optimization is required. and roots of the equality constraints are the only candidate point for the optimum. So this is a very important point in while you are formulating or while you are making the standard optimization design problems. Okay, so be careful. The number of equality constraints at the end, you can conclude that the number of equality constraints should be always less than n, or where final maximum extent it might be equal to the number of design variables, but it cannot be greater than number of design variables. Please remember this. And the third point that needs to be observed is the number of inequality constraints. So while there is a restriction on the number of independent equality constraints, there is no restrictions on the number of inequality constraints. However, the total number of active constraints must at the optimum be less than or at most equal to the number of design variables. This is a very important point. So we have in the standard optimization model, so apart from the equality constraints, we also indicated the inequality constraints. But in optimization model or optimization problems, so we don't have any restrictions on the number of inequality constraints over here. So as unlike what we had for equality constraints, so here there is no restrictions on the number of independent inequality constraints, and there is no restriction. Okay, so here in the inequality constraints. However, the total number of active constraints satisfied at the equality must at the optimum be less than or most equal to the number of design variables. So active constraints and inactive constraints I will discuss in the later part. So active constraints, then the total number of active constraints means which will go into equal to the satisfying the equality conditions. It's a less than or equal to or greater than or equal to. So the two conditions. So less than or equal to. So the constraints which satisfies the equality, they are called active constraints. And these active constraints should be less than or at most equal to the number of design variables. This is what they will going to say. Okay. So this is the third important observations what we're going to make it from the standard optimization model. Okay. And the fourth point is the unconstrained problems. Some design problems may not have any constraints. These are called unconstrained. Those with constraints are called constraints. See, sometimes what happens, you might find there will be no constraints. Okay. So, of course, there are certain cases you will going to find it out. Of course, we are going to discuss that in later part. So, some problems, when you are just formulating the optimization problems or design optimization problems or models, so you will find, so there will be no restriction, there will be no constraints on the problems. So, in such cases, those problems we are going to treat it as an unconstrained optimization. So where there is no constraints at all. So if the problem or a model does not have any constraints, then it is said to be an unconstrained problem, and those with the constraints, they are said to be a constraint. Okay. So this is the fourth observation. And the fifth observation over here is linear programming problem. If all the functions f of x, j of x, and j of x are linear in design variables x, then the problem is called linear programming problem. And if any of these functions is non-linear, the problem is called non-linear programming problem. So when you are formulating the functions, either it is an objective function or whether it is a constraint function, right? So that function will be always have a relationship with respect to the design. This is what I was talking in the first part. So either it is a cost function or whether it is a constraint function, it should depend on the design variable. It means that once you formulate the function, So that function should be have a relationship with respect to the design variables, what you have identified and what you have defined. So if this relationship between either the f of x, the first function, hj of x, it is a equality constraint function, j of x, it is an inequality constraint function. These functions, if you have a linear relationship with the design variables, then that problem you go to treat it as a linear programming. And if these functions is non-linear, then the problem is said to be a non-linear programming. So there are different approaches for getting the solutions for linear programming and non-linear programming. Okay, so those things later part of the syllabus we're going to be discussing how to solve or how to get the solution for a linear programming problems and non-linear programming problems. So be careful and be observe. So what is the relationship? And because so nobody will going to tell you which is a linear and which is a non-linear. So you should identify. So based upon what type of relationship the function, the objective function having relationship with the design variables and constraint function having a relationship with the design variables. Based upon that, you come to the conclusion that this is a linear programming problem, and I can use the techniques which are involved for optimization technique which are required for solving a linear program. So you can implement and you can get a solution. Like that, similarly for non-linear programming. And the last point what we discuss here is scaling of problem functions. So it is important to note that if the cost function is scaled by multiplying it with a positive constant, the optimum design does not change. However, the optimum cost function's value does not change. Also, any constant can be added to the cost function without affecting the optimum design. Similarly, the inequality constraints can be scaled by any positive constant and the equalities by any constant. This will not affect the feasible region and hence the optimum solution. All the foregoing transformations, however, affect the values of Lagrange multipliers. Also, performance of numerical algorithms for solution to the optimization is affected by these transformations. Means, what it says is, I think when we solved the problems, I think you might have seen, sometimes we have multiplied the cost C for cost function. So somewhere you are not multiplied, in some problem we have multiplied the constant value that is C. So means the cost functions can be scaled by multiplying it with a positive constant. It's very important here, it should be a positive constant only, not a negative constant should be multiplied. And when you multiply or when you just multiply with a positive constant, the optimum design does not change and optimum cost function value does not change. And also, you can add the positive constraint to the inequality constraints by scaling it down, just like how we did in the previous problem. So in the last formulation, so if you remember, we multiplied 100 number of cabinets and we have multiplied the 100 to the each cost function. So just if you remember, if you just go back to the last class what we discussed, the design of a cabinet. So there you can see the third formulation. So cost function you have multiplied by the 100. So that is the constant what you are multiplying. So it does not make any difference to the cost function or it does not make any difference to the optimum design. Okay, and of course, nothing will be changed in this. And also, you can scale the inequality constraints also by adding the positive constants and equalities for any constant. So equality, you can add anything, whether it is negative or positive, not an issue. Okay, these things will not affect the feasible region and hence the optimum solutions. Okay. So of course, the next part I want to skip at this point because I will discuss those things later. So this is the important observations what you're supposed to make with respect to the standard optimization, design optimization. So this is very, very, very important for the subject point of view, because once you know how to formulate the problem and how to bring it into a standard design optimization model, and you should know what are the observations what I have done. So whether the number of equality constraints or the number of inequality constraints, so what type of problem it is, whether it is a linear programming or non-linear programming, whether the problem has got constraints or not. So based upon that, so these are all the observations what you're supposed to do once you formulate from the problem description, once you formulate the optimization design problem and put it in the form of a standard model. Then it is easy for us to get the solution based upon what type of programming problem. Okay. So this is what I wanted to convey at the first point of in today's class. Okay. Next, I will just start with classification of optimization problems. See, of course, there are plenty of classification. There are different classifications in can and different headings. Okay. So the first classification is based upon the constraint. So constrained optimization problem, and second one is called unconstrained optimization. If we find a optimization problem with the constraints, whether it is equality constraints or inequality constraints, then it is said to be a constrained optimization. So that's what I was discussing in the previous slide. And if we find there is no constraints in the optimization problem, then it is said to be an unconstrained optimization. Okay. So second one is the nature of design variable. So based upon the nature of design variables, so we can have two. One is a static optimization problem, and second one we call it as dynamic optimization. So in this case, static means, so what kind of design variables you have identified and you have defined. So if the design variables are static, means it does not change with respect to the time, then it is said to be a static design variable. And such problems we call it as static optimization problems. And if anything which changes, see, if a simple example, the two diagrams what I have shown over there here. You can see here the two sketches, two diagrams what we are showing here. So what it is showing is, one is load P is acting, it is a cantilever beam. Load P is acting over here, right? And this is the depth and this is the width and this is the length of the beam. So in this case, either the length or depth or whether it is a width does not depend upon the time. Whatever the load you will go into act, so it will go into be having this. But when you look at here, in the second case here, D is a function of T and D is a function of T. So means both the depth as well as the width or the functions of a time, means they depends upon the time. So here the two design variables are width and the depth. And if this width and the depth are of time functions, okay, then it is said to be a dynamic optimization problem. If these design variables is not depending upon the time, then it is said to be a static optimization problem. So this is the second classification based upon the nature of design variables. Okay. So if the design variables depends on the time function, they are called dynamic optimization problem. And if they don't depend on the time, then it is said to be the static optimization problem. Then classification of optimization problems based on physical structure of the problem optimal control problems and non-optimal control problems. I will discuss this feature in the future, the next slides. And the second one is nature of equations involved. Nonlinear programming problems, geometric programming problems, quadratic programming problems, and linear programming problems. So this is the second classification. This is the fourth classification, which depends upon the equations. Means, sorry, the relationship existing between the function and the design. That's what I was talking in the previous slides, in the previous slides, where the cost function depends, have a linear relationship with respect to the design variable. It is to be a linear programming problems, and if not, then it is said to be non-linear programming. Apart from these two, linear and non-linear, we have another one, two important, what we call it as a geometric programming problems and quadratic programming. So we're going to discuss these things in details in the future. Okay. The next is classification based upon the permissible values. Permissible values. That is integer programming problems and real value programming problems, and deterministic nature of the variables, stochastic programming problems, and deterministic programming. So basically, the word we will just discuss permissible values means the design variables can have an integer value. If the permissible values for the design is of integer, then it is said to be integer programming problem. In the previous problems, what we discussed everything, the design variables I is equal to 1 to n. So where the I value is equal to having integer values, then it is said to be an integer programming problems. And if the design variables can have a real values or real numbers, then such type of problems we call it as real value programming. I will discuss the nature of this next classification is stochastic and deterministic in the latest. Next comes the classification based upon separability of functions, separable programming problems, and non-separable programming functions or problems, and the number of objective functions, single objective programming problem, and multi-objective programming. So let us discuss these things one by one. Let us take geometric programming. So I was talking about the nature of function, the equations they have. A geometric programming problem is the one which objective function and constraints are expressed as a polynomial in X. Whether you have discussed the word, I think you might have discussed a polynomial, whether you have discussed polynomial or not. So please look at this. So geometric programming, please look at mathematics and you can just understand what is a polynomial. The monomial functions, so this is the standard programming, the geometric programming what we are having. The polynomial function is a sum of monomials. And geometric programming, so it is a standard geometric programming problem what we are having here. Okay, so here a geometric programming is the one where the objective function and constraints are expressed as polynomial in X. Please look at here. So this is the polynomial, what we call it as. So polynomial means so here we are having the polynomial. So this we can understand. Okay, so please go through the textbook and you can just get what is the polynomial. Okay, and next is the quadratic programming problem. So where quadratic programming problem is a non-linear programming problem with a quadratic objective function, and the linear constraints, and it is usually formulated as, this is a standard form of quadratic programming problem. It is a non-linear programming problem with a quadratic objective function and linear constraints, and it is usually formulated in this form. So this is what we call it as the quadratic programming problem. Okay. Then optimal control problems. An optimal control problem is a mathematical programming problem involving a number of stages where each stage evolves from the preceding stage in a prescribed manner. So this is what we call it as optimum control problem. In the sense, each problem, the number of stages, each stage will evolve from the preceding stage in the prescribed manner. So such type of mathematical programming, we call it as the optimal control programming problem. So this we can see here is, so it starts from one control points, 1, 2, 3, like this, it will be keep on going. In the sense, each stage is evolved. So second stage is evolved from stage 1, third is evolved from 2, like this. Each stage is evolved from the preceding stage in the prescribed manner. Such type of problems we call it as the optimal control problem. And it is usually described by two types of variables, the control control and the state variables. The control variables define the system and down the evolution of the system from one stage to the next stage, and the state variables describe the behavior of the status of the system in each stage. So this is how we have optimum control problem. So this is how we will go into formulate the state the optimum control problem. Is a set of control or a design variables such that the total objective function over all stages is minimized subject to a set of constraints on the control and state variables. So this is the optimal control problem. This is a standard model for optimum control problem, where x is the ith control variable and y is the ith control variable. So for this we can understand. Next comes integer programming problems. If some of the design variables of an optimization problem is restricted to take an integer values, the problem is called integer programming problem. And if it is permitted to take any real value, it is said to be real value programming problem. Same thing, that's what I was discussing. Stochastic programming is an optimization problem in which a sum of all the parameters, some or of all the parameters are probabilistic. So it is non-deterministic. In other words, stochastic programming deals with the solution of optimization problems in which some of the variables are described by probability distribution. So the way I find the probability concept in this type of problem. Separable programming problems. A function is said to be separable if it can be expressed as a sum of n single variable functions. If a function is expressed as a sum of n variable functions, then it is said to be separable programming functions, and the problems which are involving such functions, we call it as separable programming problems. So this is a standard format for separable programming problems. Next comes multi-objective programming problem. Multi-objective programming problem can be stated as follows, which we have here. Okay, so this is standard form for multi-objective programming problem. Okay, so for time being, hello my dear students. So my time is running out. So for time being, I will just stop at this point. In tomorrow's class, so we will start discussing some more optimization concepts and how to define the local and global minima, the sufficient and necessary conditions, all those. So before that, I want you people to do the assignment problems, what I have been posted in the Google Classroom. Okay, so please do that and get it ready with the solutions. Everything is very important for me. So once you get that, then only we can solve the problem. Okay. So thank you very much for